Look up on a clear, moonless night, far from city lights, and you'll see them, thousands upon thousands of stars, scattered across the darkness like diamonds on black velvet. They seem eternal, don't they? Fixed, unchanging, as permanent as anything in the universe could be. But here's the truth that will change how you see every star forever. Stars aren't eternal twinkles in the cosmic dark. They are born. They live dramatic lives filled with violence and beauty, and they die, sometimes quietly, fading like embers, and sometimes in explosions so brilliant they outshine entire galaxies. Every star you've ever seen is at some stage in this grand drama, that steady point of light you wished upon as a child. It might be a newborn, just igniting its nuclear fires, or a middle-aged traveler like our sun, steadily burning through its fuel, or an ancient giant in its death throes, swelling to monstrous size before its final spectacular curtain call. And here's the most beautiful part, the most profound connection between you and the cosmos. You are made of stars, not metaphorically, literally. Every atom in your body, heavier than hydrogen, was forged in the nuclear furnace of a dying star, then scattered across space in a supernova explosion, eventually coalescing into planets, oceans, and you. Carl Sagan said it best: "We are made of star stuff." Tonight, we'll discover why that's not poetry. It's physics. Join me as we follow a star's journey from birth in a stellar nursery to death in cosmic fireworks, a cycle that has repeated trillions upon trillions of times across 13.8 billion years of cosmic history. We'll visit nebulae where stars are born by the thousands, witness the steady burn of stellar maturity, watch as giants swell to impossible size, and finally, we'll see how stars die, seeding the universe with the elements that make life possible. The story of stars is the story of everything, including us. Let us begin at the beginning, in the dark, cold clouds where starlight first ignites. Imagine a cloud. Not a cloud of water vapor like those that drift through Earth's atmosphere, but a cloud of gas and dust stretching light years across space. Hydrogen and helium left over from the Big Bang, mixed with heavier elements cast off by previous generations of stars. These are nebulae, the stellar nurseries, the cosmic clouds where stars are born. For millions of years, these clouds drift through space, vast and diffuse and cold, just a few degrees above absolute zero. But gravity never sleeps. Gravity is patient. And slowly, inexorably, gravity begins to pull the cloud together. Perhaps a nearby supernova sends a shockwave rippling through the cloud, compressing it. Perhaps the cloud simply reaches a critical mass where gravity overcomes the outward pressure of heat. Whatever the trigger, the cloud begins to collapse. And here's where the magic begins. As the cloud collapses, it fragments into hundreds or thousands of dense knots, each one a future star. As each knot pulls more material inward, it spins faster, like a figure skater pulling in their arms. A disk of material forms around the collapsing core. Planets will eventually form in that disk, but that's another story. The core grows denser, hotter, more compressed. The atoms are being squeezed together with such tremendous force that they begin to move faster and faster, colliding with ever-increasing violence. The temperature climbs, thousands of degrees, then tens of thousands, then millions of degrees. And then, ignition. At 10 million degrees Celsius, hydrogen nuclei are moving so fast that when they collide, they overcome their electromagnetic repulsion and fuse together, forming helium. This is nuclear fusion, the same process that powers hydrogen bombs, but controlled by gravity and sustained over billions of years. A star is born. This newborn star, called a protostar in its earliest stages, blows away the remaining gas and dust with powerful stellar winds, revealing itself to the universe. What was once a dark cloud now blazes with the light of nuclear fire. You can see this happening right now, tonight, if you know where to look. The Orion Nebula, visible to the naked eye as the fuzzy middle star in Orion's sword, is a stellar maternity ward just 1,350 light-years away. Thousands of stars are being born there right now as you watch. It's like peeking into a celestial delivery room, witnessing the universe creating its future. And here's a humbling thought. Our sun formed this way. 4.6 billion years ago, in a cloud much like the Orion Nebula, gravity pulled together a knot of gas that would become our star. The leftover disk formed the planets, including the one we call home. Every photon of sunlight that has ever warmed your face, every ray that has ever powered a leaf or brightened a day, began in that ancient ignition when our sun first achieved fusion. Stars are born, and now they must live. Welcome to the main sequence, the longest, most stable phase of a star's life. This is stellar adulthood, and it's where about 90% of all stars spend most of their existence. In the core, hydrogen fuses into helium, releasing tremendous energy. This energy pushes outward, creating pressure that exactly balances the inward pull of gravity. The star achieves equilibrium, a delicate balance between the crushing force of its own mass and the explosive power of nuclear fusion. It is a nuclear power plant, floating in space, converting mass directly into energy according to Einstein's famous equation, E equals mc squared. Every second, our sun converts 600 million tons of hydrogen into helium, and in that process, 4 million tons of matter simply become energy, the light and heat that make Earth habitable. But here's where stellar lives get interesting. Not all stars are created equal, and the mass of a star, how much material it gathered during birth, determines everything about its life and death. Small stars, with less than half the sun's mass, are the misers of the galaxy. They burn their hydrogen fuel so slowly, so carefully, that they can live for trillions of years, longer than the current age of the universe. Some red dwarf stars born in the earliest days of the cosmos are still in their infancy, with tens or hundreds of trillions of years still ahead of them. Sun-like stars, average stars, neither particularly massive nor particularly small, burn moderately. Our sun will live about 10 billion years on the main sequence. It's currently middle-aged at 4.6 billion years old, with another 5 billion years of steady burning ahead. But massive stars, stars with 10, 20, 50 times the sun's mass, they are the rock stars of the galaxy, brilliant, spectacular, and doomed to die young. The bigger they are, the hotter they burn. A star 20 times the sun's mass doesn't live 20 times longer. It lives 20 times shorter. Maybe just 10 million years total. It's as if they're burning through their fuel with reckless abandon, racing through their lives in a cosmic blink. Why? Because fusion rate scales dramatically with mass and temperature. A massive star's core is so hot, so dense, that fusion proceeds at a furious rate. The star must burn brighter to balance the immense gravitational pressure trying to crush it. So you see the cosmic irony. The largest stars, the most massive and luminous objects on the main sequence, are also the most short-lived. They burn bright and fast, like cosmic fireworks, exhausting their fuel in mere millions of years, while their smaller cousins will outlive them by factors of millions. But whether a star lives for 100 billion years or 10 million years, eventually the same fate comes for all of them. The hydrogen runs out, and when it does, the star must face its mortality. Imagine you're a star. For billions of years, you've been fusing hydrogen in your core, maintaining that perfect balance between gravity and fusion pressure. It's all you've ever known. It's all you've ever done. And then, the core runs out of hydrogen. Fusion slows, stops. The energy pushing outward weakens. And gravity, patient, relentless gravity, begins to win. The core contracts. But something remarkable happens. As the core contracts, it heats up. Gravitational energy converting to thermal energy. It gets hot enough that hydrogen in a shell around the inert helium core begins to fuse. The star now has a new energy source, but it's unstable, fluctuating, producing more energy than before. All that energy pushes the outer layers outward. The star swells, and swells, and swells. Our sun will do this in about 5 billion years. It will expand beyond Mercury's orbit, beyond Venus's orbit. And yes, it will likely engulf Earth, vaporizing the oceans, incinerating the continents, reducing our entire world to ash and vapor in its outer atmosphere. This is the red giant phase. The star has become enormous, hundreds of times its original size, but its surface has cooled to a mere 3,000 degrees Celsius, giving it that distinctive red color. It's like a balloon expanding as you blow air into it, the same material spread over a vastly larger area. Inside the core, temperatures continue to climb. When they reach 100 million degrees, something new ignites: helium fusion. 3 helium nuclei smash together to form carbon. Sometimes another helium fuses to that carbon, making oxygen. This is where the elements that make life possible are forged. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, all of it was created in the cores of dying stars like this one. For sun-like stars, this is as far as it goes. The core never gets hot enough to fuse carbon. But for massive stars, those titans with 8 or more solar masses, this is just the beginning of a remarkable process. Layer upon layer of fusion begins. Carbon fuses into neon and magnesium. Neon fuses into oxygen. Oxygen into silicon. Silicon into iron. The star develops an onion-like structure with iron in the very center, surrounded by layers of silicon, oxygen, neon, carbon, helium, and hydrogen, each layer fusing into the next heavier element. Look at Betelgeuse, the red supergiant marking Orion's shoulder. You can see it with the naked eye. It's one of the brightest stars in the night sky, distinctly orange-red. Betelgeuse is in its death throes right now. It's already fused through hydrogen and helium. It's creating carbon, oxygen, and heavier elements in its core. And at some point, tomorrow, or 10,000 years from now, it will reach the final stage. Ancient cultures told stories about Betelgeuse. The Egyptians associated it with the god Osiris. Aboriginal Australians saw it as a young man who became the firebringer. They were watching, unknowingly, a ticking time bomb. A star approaching the most spectacular death the universe can offer. And when Betelgeuse finally explodes, it will be visible in daylight on Earth. For weeks, our sky will have 2 bright objects in it, the sun and a brilliant new star where Betelgeuse once stood. But we're getting ahead of ourselves. Let's talk about how stars die. Death comes to all stars. But the manner of death, the final act in this cosmic drama, depends entirely on mass. Small and medium stars go gently. Massive stars do not. For stars like our sun, stars with less than about 8 solar masses. The end comes with a whimper, not a bang. When the red giant has exhausted its helium fuel, fusion stops for good. The core can't get hot enough to fuse carbon. There's no more energy to hold the star up against gravity. The core collapses, but only to a point. At tremendous densities, a quantum mechanical effect called electron degeneracy pressure kicks in. Electrons simply refuse to be compressed further. It's not a matter of force, it's a matter of fundamental physics. The Pauli exclusion principle says no two electrons can occupy the same quantum state. The collapse stops. What remains is a white dwarf. A white dwarf is bizarre beyond imagining. Take the mass of the Sun, 300,000 times Earth's mass, and compress it into something the size of Earth. A teaspoon of white dwarf material would weigh about 15 tons on Earth's surface. It's not fusing anything. It has no internal energy source. It's simply cooling, a cosmic ember, radiating away its residual heat over billions upon billions of years, eventually becoming a cold, dark cinder, a black dwarf. But before it becomes a white dwarf, the red giant sheds its outer layers in a beautiful display called a planetary nebula. Glowing shells of gas illuminated by the dying star's ultraviolet radiation, spreading outward into space. These are some of the most beautiful objects in the sky. The Ring Nebula, the Helix Nebula, the Cat's Eye. This will be our Sun's fate. 5 billion years from now, the Sun will puff off its outer layers, perhaps creating a beautiful nebula that some distant civilization will observe and admire. At the center will remain a white dwarf, the compressed core of what was once our life-giving star, slowly cooling in the darkness. But massive stars die differently. Remember those onion layers? Hydrogen, helium, carbon, oxygen, silicon, and finally, at the very center, iron. Iron is special. It's the most stable nucleus in the universe. Fusing lighter elements into iron releases energy, but fusing iron into heavier elements requires energy. It's endothermic. When the core becomes iron, fusion not only stops producing energy, it starts consuming it. The core is doomed. It collapses. In less than a second, a core the size of Earth compresses to something the size of a city, about 20 kilometers across. The protons and electrons are squeezed together so hard, they merge into neutrons. A flood of neutrinos erupts outward, so many neutrinos that despite their almost non-existent interaction with matter, they blow the rest of the star apart. This is a supernova, a star exploding with the energy of 10 billion suns. For a few weeks, this single dying star outshines its entire galaxy. If you were to gather all the light from 100 billion stars and focus it into one point, that's how bright a supernova is. The explosion is visible across millions of light years of space. And in that explosion, something miraculous happens. The tremendous energies, the crushing neutron cores, the shock waves, the high-energy particle collisions, create elements heavier than iron, gold, platinum, uranium, lead. Every heavy element in the universe, every atom of gold in every ring, every atom of uranium powering nuclear reactors was created in the death of a massive star. The explosion scatters these elements across space. They mix with nebulae. They become part of the next generation of stars and planets. Our Sun is a second or third generation star, made partly from the ashes of previous stars. Earth formed from a disk of material that included those scattered elements. Your body is made of atoms forged in stellar furnaces billions of years ago and scattered across space in supernovae. We are, quite literally, the universe made conscious. Star stuff contemplating stars. But what happens to the core? If the original star was between about 8 and 20 solar masses, the collapsed core becomes a neutron star, a sphere of neutrons so dense that a sugar cube-sized piece would weigh as much as Mount Everest. These objects spin rapidly, sometimes hundreds of times per second, with magnetic fields trillions of times stronger than Earth's. Some neutron stars beam radiation from their magnetic poles. As they spin, these beams sweep across space like cosmic lighthouses. When the beam points at Earth, we detect a pulse. These are pulsars, nature's most precise clocks, some ticking with millisecond accuracy. But if the original star was massive enough, more than about 20 solar masses, even neutron degeneracy pressure can't stop the collapse. The core implodes beyond the neutron star stage. Gravity becomes so strong that escape velocity exceeds the speed of light. Space itself warps into a one-way trap. A black hole is born. Nothing, not even light, can escape. The star has literally collapsed out of the universe, leaving behind only its gravitational footprint, a region of space-time so warped that it forms an eternal prison. And here's a beautiful irony. Type 1, a supernovae, a specific kind of supernova that occurs when a white dwarf accretes matter from a companion star and exceeds a critical mass, are so consistent in their brightness that we use them as cosmic standard candles. By comparing how bright they appear to how bright they actually are, we can measure distances across billions of light years. These dying stars have become our measuring sticks for the universe itself. And so the cycle continues. Stars are born in nebulae enriched by previous generations. They live their lives, short or long, quiet or spectacular, and they die, returning their enriched material to space, seeding the next generation. This has happened over and over, billions upon billions of times, since the first stars ignited just a few 100 million years after the Big Bang. Those first stars, called population 3 stars, were made of only hydrogen and helium. No carbon, no oxygen, no iron. They lived, died, and scattered the first heavy elements into space. Second-generation stars incorporated those elements, created more, and scattered them in turn. We are the beneficiaries of countless stellar cycles. The atoms in your body have been through multiple stars. You are ancient beyond measure. Your atoms are nearly as old as the universe itself, forged in stellar furnaces, scattered in supernova, reformed into new stars and planets, over and over. The iron in your blood was forged in a massive star and scattered in a supernova explosion. The calcium in your bones was created in a dying red giant. The oxygen you're breathing right now was fused from helium in a stellar core billions of years ago. Carl Sagan taught us that we are a way for the cosmos to know itself. And now you understand why. We are not separate from the universe. We are the universe, rearranged into a form capable of wonder. Stars' lives mirror our own in a profound way, full of drama, transformation, and legacy. They are born from chaos, live with purpose, age with grace or violence, and die leaving behind gifts for the future. Every time you look up at the night sky, you're seeing the universe in all its life stages. That bright blue star, a young giant burning furiously. That red star, an ancient elder in its death throes. That steady yellow star, a middle-aged traveler, much like our sun. And when you look at your own hand, you're seeing the legacy of stars that died before our sun was born. So I ask you, which stage of stellar life fascinates you most? The violent birth in stellar nurseries, the steady burn of the main sequence, the dramatic swelling of red giants, or the spectacular death in supernovae and the exotic remnants left behind? Subscribe to This Week in the Sky to explore more of these stellar stories. Join us as we continue to explore the cosmos, from the smallest particles to the largest structures, from the beginning of time to the ultimate fate of the universe. And remember, the next time someone tells you to reach for the stars, remind them that you're already made of them. Clear skies, fellow travelers, and keep looking up. The stars are where we came from, and in understanding them, we understand ourselves.